All right, so let's take a look at what is pressure. So the interesting thing is, even our atmosphere has pressure. For every square inch that's on you, a square inch on my hand, on the tip of my finger, on the back of my hand, on my head, my temple, my chin, my neck, my shoulders, wherever, every square inch of our body is experiencing 14.7 pounds of pressure, which means literally, when you think how many square inches there are on a human body, there's tons of pressure pushing in on us. And the fact that we don't collapse is because we're pressurized for this atmospheric condition. Without a skeletal system, you wouldn't be able to stand upright. You know, if you go out into the International Space Station and you're there long enough, now you do have to do some exercises where they actually have like bungees where they pull you down and you run to try and help simulate some gravitational pull. But almost all come back taller, measurably taller, because their spine decompresses. Now, granted, when they're back on Earth and gravity pulls them down more, that gravity, recompresses the spine. So, but for a brief period, you are definitely a little bit taller. So, because we're pressurized, we can survive the surface. But if we go into outer space, we have to have a spacesuit on, because without all that pressure, all the gases in our bodies would come out of solution. And if you do that, like if you're scuba diving, that's called the bends. Pressure also creates, you can create a cloud with a difference in pressure. You can hold someone up with a difference in pressure. And I'm not going to play, this is, you can go back into the notes. Remember, this is the card, you flip it upside down. Um, and atmospheric pressure, there's more, you know, air pressure pushing up on that card than the water is. It's the same thing if you take a straw and you put your finger on the top of it and lift it up, you'll pull the water out. And as soon as you let the air off, the air pressure from the other side pushes the water back down. So that's what he's doing with that. He just put the card and you can get that to stay. Now, if you have a good pressure chamber and you put just a little bit of water vapor in there to get some moisture, and then light a match and put it out inside there so that you get just a little bit of dirty particle. Because remember, clouds have to have water particles, and clouds have to condense on um, dirt in the atmosphere. So that's what he did by putting the match in there. He's just getting a little bit of smoke in there for the water molecules to condense on. Now he's going to take the pressure out. And once he does that, and this of course is going to stop, so we're going to go here. I should have remembered that we only get about 2 minutes. So now he's going to put that in. He's going to take and remove the pressure, and then once he's got enough pressure out, he's going to quickly put the pressure back in. And because all of a sudden you've increased the pressure, you get a cloud to form, because all that water molecule recondense quite quickly and become solid. In this case, the vapor goes to droplets. You can also do something else with it. If you take a cylinder, like coming up here, and you take the bottom here, that piece of plastic is actually not attached except for anything other than the fact that they're removing the air from inside, creating a negative pressure. We call it a vacuum. Actually, there's no such thing as vacuum technically in science. It's a negative pressure, but we all know what that means. And so what happens is there's enough square inches pushing up on that surface at 14, almost 15 pounds per square inch, that this guy will be able to hang from that and not fall down, because it's not going to release until they put the pressure back in. And once he puts the pressure back in, he's going to fall, because now all of a sudden it was equalized pressure. So you can do the same thing with a can. We do this in class, where you take a pop can and we heat it up and put some water vapor in there, and then quickly flip it upside down into cold water. This is the same thing. What they did is they took a vacuum and they pumped all the air out of it, and it could not survive the atmospheric pressure. Now think how big and heavy duty that metal is on that tanker, but it can't survive the atmospheric pressure. When you do, remember on the last unit we had the picture of the ostrich feathers and the bowling ball basically being dropped from the same time, but in that huge vacuum chamber? Those walls were like 6 or 8 feet thick to survive the atmospheric pressure pushing in on it when they removed the air from inside. So the same thing happens actually if you go underwater. If you go underwater, you actually obviously have to take scuba gear, but there's a lot of pressure, like 10 times. If you go down 100 feet, it's something like 10 times the pressure.
When a diver goes deep underwater, the pressure acting on the diver's body increases. While normal air pressure at sea level is about 100 kilopascals, the pressure exerted by water can be greater than 10 times that of the air when a diver reaches 100 meters. The compressed air that the diver is breathing can easily dissolve into liquids inside the diver's body. So the deeper a diver goes and the longer a diver stays underwater, the more oxygen and nitrogen molecules enter the diver's bloodstream and tissues. When the diver begins to surface, the pressure on the diver's body decreases, and bubbles of nitrogen and oxygen begin to expand. Nitrogen bubbles are dangerous to divers. If the diver surfaces too quickly, bubbles of nitrogen can expand and become lodged in the diver's bloodstream, nerves, and tissues, and cause the intense pain that many divers know as decompression sickness, or the bends. Some divers suffering from decompression sickness can benefit from being placed in a hyperbaric chamber, an enclosure in which the pressure can be gradually increased and then decreased, allowing the nitrogen bubbles to be reabsorbed and then slowly released without forming large bubbles.
That's how you get rid of the bends. Right after you're done watching this set of notes, I'm going to give you another Edpuzzle to watch, which is about ear pressure and how does ear pressure work when your ears pop. And if you've ever been on a plane, you want to chew gum or you want to swallow, you want to pinch your nose, and basically what you need to do is equalize the pressure. The pressure is changing inside your ear compared to what's in there as they pressurize the cabin, and as they come down, it changes as well. Even if you go down a big hill, sometimes you can experience that change in pressure. And that video will actually explain how the ear works to pressure, keep the pressure equalized. So as altitude increases, the higher up you go, the pressure decreases. They're inverse, because think about it. Down here at sea level, you have all of the atmosphere above you pushing down on you. But if you're at the top of the mountain, you don't have all the stuff below you pressing down, and the air molecules can get farther and farther apart. So if you go to the top of Everest, almost everyone that goes and climbs to the top will bring oxygen canisters. It is so laborious on the body that once they use the canister, they don't actually bother bringing it down because it takes too much energy to carry that, and as much weight as they can get rid of, they can. So there's litter, like literally all over Mount Everest. In fact, if you die on Everest, that's your grave site. So if you choose to climb it, you actually can come across people that didn't make it back down. And it's because as you get to the top, they just couldn't get enough oxygen in. Their body couldn't handle it because there were so few. You could breathe it in, but the molecules are so far apart, you just couldn't get the volume of oxygen needed. So as altitude increases, pressure decreases. As altitude decreases, pressure increases, inverse. And obviously, if you go underwater, not only do you have all the atmosphere above you, but now you've got all the water on top of you as well. So a barometer is what we use to measure air pressure. It can be mercury barometer, or it can be an aneroid barometer, which is a metal coil. And either one can tell you if the pressure is rising or falling. And this is a quick review from last year, so I'm not going to spend a ton of time on this, but remember, everything flows from high pressure to low pressure. Cold, densely packed together, low to the ground air spreads out in all direction, kind of like a water balloon exploding, going out to fill its fine level. And warm, hot air rises, and as it rises, it gets warmer and it goes farther apart, and as it rises, it leaves a void underneath, so that creates even lower pressure. So the cold air flows to the warm area to fill in where the warm air is rising, and you get convection currents going. And it's a difference in pressure. That's what causes our wind. The closer those pressure bars, those isobars, are together, the stronger the winds, which you could see here. We're going here. This is a low pressure cell because it's 992 millibars, I believe. And if we're up here, we're at 1008. And so that's lower as we go towards here. We went from 1020 to 1024, so that's higher pressure. You're not going to have a lot of wind between these isobars because they're pretty far apart, but right here, these gradients are pretty steep. In other words, they're very close together. you would have stronger winds there. Talk about pressure. Let's look at this pressure. See if we can get this to play. So this is an elephant, and it happened to be Cambodia, and it happened to be elephants' mating season, and elephants become a little more active, and you don't want to be that car right now, because think how much pressure is being exerted on the hood. An elephant sitting on a car is a whole different thing than your posterior sitting on a car, and that foot is exerting a massive amount of pressure. Now the people in the car were actually okay, but he does break off the mirror here shortly as he climbs up on it and over it. So remember, pressure is force divided by area. He has a lot of force because gravity's pulling him down. Now these people saw what happened. They're finally getting smart enough to, back away. I would not really want to be the person on the scooter at that point, but big pressure, well, basically took the hood off that car. So quick review. We went through this on the other set of notes. Pressure is force divided by area and measured in pascals. We abbreviate that to capital P small a. So P equals force divided by area, where it's a small a for acceleration. It's a small a for area. A large A is for acceleration. So that's how we differentiate the two. And in the other video, I just kind of wrote it out, but you can use a small a, and P is for pressure, which, as you know, we start getting more and more different things. So if you haven't done it and want to do that for sure, make sure that you are looking at 1 Newton divided by 1 square meter, or 1 kilogram divided by 1 meter per second squared is another way to look at it, is 1 Pascal. That's what they would convert to. So here is your handy dandy formula triangle, where pascals, pressure, and area are on the bottom, and your force is up on top. And we talked about this in the other video as well. If I try and walk in snow with snowshoes, I'm probably going to stay on top. If I have tennis shoes, or heaven forbid high heels, I'm probably going to sink through the snow. The snowshoes spread out your area in a much greater area. It's kind of like trying to take the back end of this crayon and try and punch it into a bulletin board. It's got such a big surface area, it's spreading that area out. It's not going to go through the board very well, where a tack would. And I just think the elephant's funny. This is the same as that other one. These are the two a little smaller demos. This is the can one we do in class, where it's, in fact, you'll do this again in chemistry. You'll see that demo a couple times. My nephews actually went to school in Wayzata, and they, in 6th or 7th grade, they had to design and conduct a scientific investigation, going through the scientific method. One of them designed a project where they wanted to find out, if you were going down a water slide, what would be the best material to give you the least amount of friction to slide faster. So we had a whole ramp set up. And the other one wanted to test which would be the best marshmallows to use in a s'more. And luckily enough for them, they happened to have an aunt who is a science teacher with a fully stocked science classroom. So they came in one day after school, and we did their experiment and recorded it. And what we found out with the marshmallows is, the cheaper the marshmallow in that test that we did, the bigger they got as they roasted, because there were more air trapped in that marshmallow. There was less sugar content and more air holes. And you can see that here as you take the pressure off. Those air bubbles actually explode out, creating an expanded marshmallow. But when you put the pressure back, they actually shrink farther, because now there's no cells in there with air bubbles to hold out the structure. You can also do an experiment where we put an Erlenmeyer flask with a balloon inside of it, and as we heat that up, the molecules inside move farther and farther and farther together. He actually used a glove here, and because those air molecules are moving farther and farther apart, they're expanding. He's going to do the same thing now with a balloon, and he's going to suck the balloon into the bottle. And he drew a little gopher, so it's called putting the gopher into the bottle trick. So as he puts that on, and you had heated air, the balloon expanded. But interestingly enough, as the beaker cools, now it's going to suck, because what he did is he put the bottle was hot when he put it on, then he put the balloon on, so it was already less molecules inside. So as that air contracts, it's actually going to suck the balloon into the bottle, and then it will actually like reverse inflate. But there's a hole in the top because it's atmospheric pressure pushing down, forcing that balloon into the bottle. And there you go, you got a gopher in a bottle using a balloon. And again, that hole is empty because atmospheric pressure pushed the balloon in, and if I reheat it, or in this case he does, we can make the balloon pop out the other way. So that's just a really quick intro on pressure. And as always, if you have questions, ask. And the classroom has fun demos, but this is the best we can do given the internet version of this. Let me know what you need.